This video is on nuclear radiation. It was Chapter 9 in the 11th edition, and it's Chapter 5 in the 12th edition. Well, radiation's been all around us forever, probably since the Earth was first formed. We have background radiation that's all around us in the rocks, in the air, and the soil. And you notice that it hasn't changed much over time. If you look at that cartoon here, our caveman is wondering what the radiation level is like in our day, and it's about 2000 AD, much the same as it was for you, mate. So let's take a look at some radioactive isotopes and some stable ones. First of all, an unstable isotope is radioactive, and what that means is that the number of protons to neutrons is not correct. And in order to correct this, the nucleus spits out bits and pieces of itself that we call radiation. And there isn't any one way to tell if an atom is going to be radioactive or not. Sometimes you can for these small isotopes, for instance, like magnesium. For elements 1 through 20, many times the number of protons and neutrons have to be the same to have something stable. And so you can see here it would be in magnesium 24, there'd be 12 protons and 12 neutrons. Now in magnesium 23 and magnesium 27, the number of protons and neutrons would be different. So it's pretty easy for elements 1 through 20. But for much larger elements, it becomes a bit difficult. For all of these, if you notice, the atomic masses are greater than the atomic numbers. So the number of neutrons is greater than the number of protons. But there doesn't seem to be a particular number you have to be stable. The most common neutron to proton ratio we see is something like 1.54 to 1. If you divide the number of neutrons by the number of protons, the closer you are to that 1.54, usually the more stable your isotope. But again, it varies so much that it's hard even to mention that. These are the different types of radiation that I'm going to be talking about. And you want to know these symbols with the type of radiation. So we'll start off with the biggest type, which is an alpha particle. Here's a Greek letter A for alpha. And this is the nuclear symbol for it. Now they have helium in here because an alpha particle has 2 protons, just like helium does. And the mass is 4, which means there's 2 neutrons as well. So this is the largest type of radiation. Now it has a charge of positive 2 because it doesn't have any electrons. A beta particle, on the other hand, matches up with an electron. So here's our symbol B for beta, and here's our symbol for an electron. No mass, a charge of -1, and you have a small e. Now you could replace a small e with B for beta, and that would be fine. And then we have a positron, which is a positive electron. So we have 0, +1 for the charge, and E again. Now we have a gamma ray. Here's a Greek letter gamma. A gamma ray is a form of light, whereas everything else here are particles. No mass and no charge for a gamma ray. We have a proton, which matches up with a hydrogen atom, so it's 1H1. And when you have a neutron, small n, which would be a mass of 1 and no charge, and a small n with it. Now you might be wondering, if these types of radiation are coming from the nucleus, how can I have an electron that comes from the nucleus? Well, an electron from the nucleus is really coming from a neutron decaying. Because if we think of a nucleus, let's say we think of a neutron, N, as being equal to, sorry about that, trying to draw on this, being equal to a proton and an electron combined together. So what can happen is this thing can break down, and you wind up getting the electron coming flying out of the nucleus. In this case, we call it a beta particle, and then the proton stays where it is in the nucleus. So in a sense, the neutron has become a proton. So that's how we can get a beta particle coming from the nucleus. Now, the beta particle is an electron, but it's not one of those electrons that we see in the energy levels. All right, let's take a look at the risk that some of these types of radiation pose. First of all, we have the greatest internal health risk is alpha particles. Inside here, inside you, if you have a substance that's producing alpha particles, it's going to be fatal for you, I'm afraid. In fact, the most toxic substance is really plutonium because it decays by releasing alpha particles. Now, but on the externally, though, get my arrow here. Externally, alpha particles can't even penetrate the skin. So, and alpha particles are really no external hazard, but a terrible internal hazard. Now, they can't even, notice they can't even penetrate the skin. Beta particles, on the other hand, could penetrate the skin, but they can't penetrate aluminum foil. So you can protect yourself that way. Now, the greatest external risk are gamma rays and X-rays and neutrons. They can penetrate the skin and cause all sorts of damage. Usually they cause damage by creating what we call free radicals, which are fragments of molecules that are looking to bond to things, and they can also create ions. And that usually leads to cancers. So gamma rays and X-rays can be very dangerous in that respect. Now, in order to stop yourself from being exposed to these, you have to protect yourself with lead and usually concrete. Neutrons, on the other hand, can penetrate all these and even look at penetrating the concrete for quite a ways. So if you get hit by a shower of neutrons, that's always fatal. Now here's a fellow that was in the news about 10 years ago. Alexander Litvinenko was a former Russian spy who moved to England when the fall of Russia happened around 1990. And he was going to write a book, a tell-all book about the Kremlin. Well, he was meeting with his agent, supposedly, at one time, and they went to have lunch, and he was poisoned. Somebody put polonium-210, which is radioactive and emits alpha particles, and they put some of this, probably a polonium-210 compound, on his salad. And he ate some of that salad, and he died less than a month later. So the alpha particles, again, externally no problem, but if you ingest a substance that's releasing alpha particles, then it's deadly. All right, let's take a look at alpha emission. So we start off by looking at this diagram here. We have a radioactive nucleus, uranium-238, and it's going to decay by releasing an alpha particle. So here comes the alpha particle. Here's the symbol for it. That's what it looks like. Now the uranium-238 nucleus then becomes thorium-234. Notice how the atomic number has changed? Therefore, the identity has changed. Now you're going to see equations that look more like this. So here we start off with our radioactive nucleus, and here are our products. Now usually one of these things will be left off, and you have to figure out what it is. But this is pretty easy to do. If you notice that we're starting with a mass of 238 on the left, it means we have to have 238 on the right. We have 234, and 4 would be 238. Same thing for the atomic numbers. We have 92 on the left, and the total has to be 92. So again, one of these particles would be an unknown, and you just have to figure out what it is. Let's say it was the thorium. So you get the numbers correct first, and then you look up the atomic number, the 90, to get the symbol. So here's one for you can try on your own. Polonium-212 decays by alpha emission. Well, a balanced nuclear equation for the decay of polonium-212. So there's the symbol for the alpha particle. And here's your equation. It's not quite finished yet. Can you figure out what the X is? So maybe you want to pause the video at this point in time and give it a try. Okay, here's the solution to it. So what we would do is try to figure out what the atomic mass and the atomic numbers are. We're already starting with 212 on the left, and we have 4 on the right. So what do we need here? 208. And then down at the bottom, we have 84 on the left, we need 84 on the right. Now these numbers give us the numbers for our X, and we're going to use 82 to determine what the symbol is. And we come up with lead-208. It's pretty easy to do it. So this is a good example of alpha decay, meaning it's releasing an alpha particle. The other type of reaction we're going to look at is called beta decay, or beta emission. So here's an example here. We have radioactive carbon-14, and it's going to release some radiation in the form of a beta particle. Here's the symbol for the beta particle. And then carbon-14 becomes stable nitrogen-14. Here's the equation that you'd be writing. Again, I'm going to do the same thing. We're starting with 14 on the left. We have to have 14 on the right. 14 plus 0 is 14. We have 6 on the left. We have to have 6 on the right. Notice we have 7 minus 1. So it's pretty easy to do. Again, one of these would be your unknown. It's very easy to mess this one up, though. I see a lot of people forget that it's minus 1, and they think of it as just 1, and they think that this is a 5, which would be all wrong. So you got to be careful when you do it. This type of reaction make radioactive isotopes from stable nuclei. Here we use a bullet, and my example here is an alpha particle, and we're going to hit the target, which is a boron atom, which is stable. So what happens is this bullet gets incorporated into the target, and then the target splits into 2 products. So you notice now we wound up making radioactive nitrogen-13, and we've got a neutron produced as well. So one of these 4 substances could be missing. You have to figure out what it is. But to use the same idea, get those numbers at the top the same. So on the left it's 4 and 10 for 14. And notice on the right it's 13 and 1 for 14. On the left at the bottom it's 2 plus 5 is 7. 7 plus 0 is 7. Okay, pretty straightforward. Next thing we're going to take a look at is how do we measure radiation. Now, you probably have seen Geiger counters before. And if not, you've seen them in movies, I'm sure. So here's how they work. We have radioactive particles like alpha and beta particles have to hit this little detector here, and then they produce an electric current that is read by the meter. You can hear clicks, so you can see the arrow moving, or even it might have a little light bulb that lights up. For every click, that means a radioactive particle is coming into that detector. So you can actually count radioactive particles. Here are some different units for radiation. We have a common unit called the Curie, CI. And a Curie it's a lot. Look at this, 3.7 times 10 to the 10th disintegrations per second. Now that means atoms decaying per second. So that's like 37 billion atoms per second. So 1 Curie is a lot of atoms disintegrating. Whereas over here, a becquerel is only 1 disintegration per second. So that would mean 37 billion becquerels equal 1 Curie. And then we have 2 units for measuring about damage to us. One is called a rad, which means radiation absorbed dose. And the other one is for measuring biological damage, which is a rem, which is radiation equivalent to man. And that's calculated by taking the rads and multiplying it by a factor that's based on the type of radiation that you're exposed to. So we have Curies and rads, and we have rems. Now we want to take a look at the factors, the different types of radiation, and how does that affect the damage. So here are our factors. Now why does the alpha particle have 20 and the first ones have only 1? Because alpha particles are so deadly to us internally. That's why it's 20. So that's why for that poor fellow Alexander Litvinenko that ate some of that polonium-210, he knew he was going to die in about a month. They're so deadly. You notice also that protons and neutrons have a factor of 10. So they're still telling you that alpha particles are twice as deadly as neutrons and protons. And beta and gamma radiation have a factor of 1. We're going to take a look at a couple of charts now. The first chart is about the annual average radiation received by a person in the United States, and the dosage is in millirems. So for natural radiation, we have the ground, air, water, food, cosmic rays from the sun, wood, concrete, and brick. All of these then we're exposed to every day. So we're kind of used to living around small amounts of radiation. Now medically speaking, we can have x-rays. We have the chest x-ray with 20, dental x-ray with 20, hip x-ray, lumbar spine x-ray, mammograms, GI series. There's a lot for that. And then even watching TV or traveling in a plane, you're exposed to radiation. Now the last one, radon, is something you should have heard about. Radon is a radioactive gas. It's a noble gas. And it's produced when uranium that's in the ground decays. But because it's a gas, it can migrate into your home and build up in your cellars. And then if you breathe in enough of this radon, it's possible that it could cause lung cancers. So when people sell homes, many times when they have an inspection done, they will have the home tested for radon gas. So the buyer of the home would have the test done. And if there was a high enough level of radon, then you either wouldn't buy the home or the seller would have to fix it so that the radon is expelled out. And the other table we're looking at is lethal doses of radiation for some life forms. So LD50 means radiation needed to kill 50% of the population. So you use a lot of radiation to kill the insects, probably because most of them are underground. And rats, probably, maybe rats are more than people. Maybe because the rats are also hidden away. We don't see them out on the surface much. But us and our friend the lowly dog here, not going to make it if there were a nuclear war.